Hi, I'm Ann Moss, and this is my Physics 2211 Lab 4 on oscillations. The purpose of this lab is to examine the motion of a mass spring system. The mass swings in an arc while it's oscillating on the spring, and a computational model was then created as a comparison to better understand not only the motion, but change in energy. The fundamental physics principles used in this lab were Newton's second law, the velocity and position update formulas, energy principle, and period of oscillation. Newton's second law equation is seen below, and it will help to derive the update formulas. The velocity and position update formulas are also seen below, and the energy principle is the total change in energy of a system is equal to the work done on a system by its surroundings and the exchange of thermal energy between the system and surroundings, and the equation is seen below, and the period of oscillation is also seen below. For the results preview, the total change in energy is 0, and the computational and experimental model are very similar, but the experimental model has a more rigid shape while the computational model is more uniform. So for the tracker analysis, the system was the Earth, spring, and mass, and there are no surroundings. And the tracker app was used to analyze the oscillating motion of the mass attached to the end of the spring over a period of time. X and Y values were outputted and uploaded to a spreadsheet. Okay, for the first part of the computational model, we have the initial conditions. The mass is given, and the initial position is based on tracker data. The system is also initially at rest, so velocity is equal to 0. The spring constant is determined by calculating the average period of time and rearranging the period of oscillation equation for K. L naught was found by setting the spring force equation to mg and solving for L naught. The system energies are just the formulas for kinetic energy, potential energy, and spring energy. So for the loop portion of the computational model, we have gravity only working in the y direction, the spring force formula, and then all forces in the system are combined to find the net force. Then we also use the update formulas, and the energy changes are found by using the energy equations and taking the final minus initial to determine the change. So for the first part of results, we have the change in energy versus change in time graph. All the energies are oscillating excluding the change in total energy. This is because there is not work done on the system by the surroundings. Therefore, W and Q equals 0, so delta E equaling work surroundings plus Q also equals 0. This is why delta E, or the orange line, stays at 0 the entire time. Okay, for the second part of the results, we have the X and Y position versus time graphs. The computational model is represented by the blue line, and the experimental is represented by the red line. The X graph has very similar results between computational experimental model with only slight differentiation at the end, and the Y graph, on the other hand, has a much greater difference between the two models. So for possible sources of error, we would have human error when using the using the tracker app, tracking the mass. It might have not been entirely accurate, and then also the period of oscillation affecting K. Only the X value was used instead of Y, or instead of averaging the two together to make it more accurate. Okay, now for the what does it mean questions. For the first question we have for the model system, is the energy principle satisfied? Justify your answer by discussing briefly your plots of energy changes. The energy system is satisfied. The change in energy should be 0 because there is no work done on the system by the surroundings, as said before. This can be seen by the orange line on the results graph as it remains at 0. For the second question, we have, using the data you obtained in Tracker, make two separate estimates of oscillation periods, first by estimating the period of oscillation from the X position data, and second by estimating the period of oscillations from the Y position data. Compare the two estimates and discuss. So the T obtained for X was approximately 1.65 seconds, and the T obtained for Y was approximately 1.56 seconds. The T for the Y data is slightly smaller than the T for the X data, and this could be a potential reason as to why the Y data is less in line with the computational model in the Y position versus time graph. The forces may be acting differently upon the objects, causing the differences.